Hello, laser geeks. Or maybe no geeks anyway. Hello and welcome. In this episode, we are going to test autogenous welding with the laser. Some call it fusion welding. I am only going up to 700 watt power, because most DIYers have the Xphotonics 700 watt version. The same rules apply to higher power laser welders. Obviously, your maximum depth of penetration depends on your unit's capabilities. I'm going to weld 1/16 sheets, performing a butt joint and a lap joint in two different ways. But first, I will laser cut 12 coupons, 3.5 inches by 1 3/4 inches rectangular sheet metal. Then I will clean it and grind one of the joining edges on each coupon. This is the most important. I'm after near perfect joints. As you can see, this is a workshop, not a lab. We are doing regular daily work you would do in your own shop or garage. Maybe the work area is larger, but the same rules apply anyway. What are we trying to showcase here? That the material is only displaced if you do not have a backing. You will have a concave weld profile if you have poor fitment. If your fitment is near perfect, you might have a very small amount of dishing, but it is measured in microns and cannot be compared to conventional welding methods. Also, you need to consider that as of yet, there is no AWS code for laser welding. It is approved if you make your own PQR, can prove the method, and have it tested in an authorized welding test facility.
Okay, let's run our first test. There is a couple of reasons why I'm doing this with thin sheets. So 16 gauge, unit 560, because most of the viewers have the smaller capacity machines. Okay, so this is something they can do all day long, whatever they have. So I'm not going all the way because then I'm going to jump the edge. Right now, I don't want to go into the details. Penetration, did we get all far away, all the way down, 100%. Yeah, that's not the point of this whole video today. There is something else, which is, as soon as I take this off I can show you. First of all, perfect because it did not stick and I already can hold it. I don't know how much is visible, but the whole idea is we didn't get all the way through very close. I'm gonna raise the power a little bit. So I'm supposed to have a concave profile over here, but I can't even grab it with my finger. So minimal. So we are talking about thousandths. I can't even measure it. I'm gonna try, but I can't. So it's just not possible because so little, so minimal. This one doesn't even fit in the discrepancies. So the person who was telling me, I don't know what the fuck I'm doing.
I couldn't get the caliper depth gauge into the weld profile because the depression was so minimal, essentially non-existent. In fact, instead of dishing inward, the material solidified with a slight upward dwell. When I scratch across it, with another coupon, the surface doesn't catch the way it would if there were a pronounced concave area. The metal pushed across of the weld profile, it catching a little bit. However, not in a valley, it catches in a ridge. According to him, I don't know what the fuck I'm talking about. I stated filler wire is not necessary in order to make a full penetration joints when you laser welding a T-joint profile or a lap joint. So here is your proof. But I will not stop here. We going to weld into a pre-cut line where material should fold into the laser cut line and create a dishing effect.
Not as bad as this gentleman was talking about. I don't know what I'm saying. Fine, I don't. So here is one test. Okay, now I'm gonna turn the unit a little bit up, and also I'm gonna try to get something longer. I can go against maybe this or something. Maybe I'm gonna fuse it to the stainless steel as well, because the hole. Interesting. I have the opposite effect.
Interestingly, I observed the opposite effect. Instead of folding into the small gap, the material once again dwelled upward and formed a ridge. Gap expected collapse, instead, ridge formed. How should I hold so it can travel like something like this? Okay, let's do this. Alright. So, I don't know if it's visible on the camera. Let me
lift 570. I did not modulate, nothing. Raw 570. Where is my plate? Come on. Alright then, okay. So raw power. I didn't tweak anything with my computer. Again, so if I touch it, it has a ridge. How this could be? I mean, come on. It has a ridge. That something is wrong with this whole test. Obviously I mounted, but it came up easily. I didn't get all the way through, but I don't want to because I don't want to mount it. At the very end, when we get to the very last pieces, then I'm gonna go to a little bit higher. By the way, if I would slow my travel speed a little bit slightly, we would go all the way through. But as I said, I don't want to mount it. So once again, it has a ridge. It doesn't have a dish. It doesn't have a dish. So, oops. I think that's the way to prove it. If I hold this, something like that, and I'm gonna shine my flashlight, if I can somehow. I might have to move my camera.
So once again, we end up with a ridge instead of a valley. That's why I have to admit, I don't really know what I'm talking about when I claim you don't need filler wire to achieve full penetration on a T-joint profile with a laser. If I'm not certain, I'll say, I don't think you need it. Or better yet, ask an expert. This is exactly what happens when an arc welder crosses into laser territory and tries to apply arc welding rules to a completely different process. For context, I bumped into laser systems from time to time. During my military work, I experienced them firsthand, and my school was promoted by Mercedes, so I had exposure to the technology. Laser welding has been around since the 1980s, used in automotive and military applications. But those were large integrated systems, not the handheld units we're working with today.
Something like this, like so, and let me shine my light. I don't see dishing. Now, maybe with this close you can see the ridge instead of dishing. Okay, so
the wire is helpful when the fitment is not near perfect, or even off by no more than 10% of the material thickness. The wire helps maintain a smooth, continuous travel speed across the joint. It also helps fill small voids if the fitment is not perfect, and it blocks escaping photons. It is recommended, certainly, but it is not mandatory, and it will not negatively affect your weld profile if you do not use it. Ultimately, it comes down to fitment. In a turning jig, you do not need it, but if you want to use it, you must be ready to calculate surface speed and match it with the wire speed. Wire is not strictly necessary. If you do not have welding wire and your parts fit together perfectly, you can weld it autogenous. Once again, you should use it if you have it, certainly, but it is not required. It remains optional, especially in do-it-yourself applications. So if you try this with your own welder and it does not work the first time, or even the 10th, the 90th, or the 200th, do not worry. It will catch up with you. You will learn it. Success depends on your settings. Start from lower power and gradually move higher. On top of that, your travel speed also plays a role. If you go too slow, you create what I call the volcano effect. The weld pool bubbles upward, gas gets trapped, and instead of collapsing flat, it forms a raised crater-like mound. I welded miles of various wires through my rig, and at the beginning I did not know all the tricks of the trade either.
And just clamp it. with 700 power. Why not? But it's too much for this material. So.
We are stepping up the power because we want this test to fail on my side.
Now we're expecting a little bit dishing because we have a hole over there. Okay.
I used less than 2 millimeters of scan and pull down wobble hertz by 30%, and our gap was 120 microns. We are expecting a large valley, so large your truck can fall into it. If you overpower your part and give it too many photons, you will end up with a minimal dishing effect. I am sure this is what the gentleman is referring to, but the dishing effect is negligible. I am measuring 0.03 millimeters. So yes, you can make a dishing effect if you do not know what you are doing. Well, let me rephrase. You are overfeeding your part with photons. The photons will chase your ferrite away, and you will end up with a dry riverbed. So let's move on to the T-joint, because that is what sparked this whole dishing effect. It has been proven that you can dish your weld bead while laser welding if you use too much unnecessary power. And this sits outside all existing code requirements, because there is no AWS code yet published for laser welding. But if we call back to AWS D1.1, the 1/16 inch rule refers to the maximum permissible root opening or misalignment tolerance in certain groove welds and fillet welds. Specifically, if the root opening or gap exceeds 1/16 of an inch, corrective action is required to remain code compliant. In our case, we are still compliant, because the dishing effect I measured was only 0.03 millimeters, a tiny fraction of 1/16 of an inch. That is less than 2% of the 16th of an inch. Measured dish is less than 2% of the AWS tolerance. Nitpick that if you can.
So I don't have a valley in the corner. How about if we do this side?
In my other video, I explained in detailed depth how the weld profile works when you weld a T-joint. If you missed it, you should circle back and watch it. It will help you understand how this process works. It is in the 700, 1200, and 1500 showdown video, right at the very beginning, and the acid test is at the end.
Okay. We bring it slower. Let's look at it. Again, I'm catching material. Sometimes it jumps over, but I'm catching material. Let's try it from this side. Catching material. Damn, it's hot.
When I tried to push the depth gauge into the corner, it caught on the dwelled metal, meaning it did not go all the way to the corner. What is causing the dwelling is excess molten metal pooling and solidifying in the joint corner, creating resistance, a ridge, or a step. But why is that? An interesting metallurgical effect is at play. Hot liquid metal attracts other nearby molten regions because of surface tension and Marangoni convection. This flow adds a small amount of density to the pool, but since there is not enough heat to drive retraction, the metal remains stable and does not collapse. It leaves a ridge. The inner lattice structure of the metal gets rearranged. Some regions become denser, while others become less dense. This redistribution locks the ridge in place. The other unwanted effect happens when you are cooking your metal. I explained the dwelling effect itself, how slow travel or excess heat causes the bead to bubble upward, trap gas, and leave a raised ridge instead of a clean profile. So, scientifically, here is why my weld beads are dwelling. Molten metal attraction. Molten pools exhibit surface tension gradients. Hotter zones have lower surface tension, so liquid flows toward them. This is called the Marangoni effect. Density and stability. The density difference is minor, but the flow is driven by temperature and composition gradients. If heat input is too low, the pool solidifies before retracting, so you do not get collapse or dishing. Lattice rearrangement. Solidification redistributes the inner lattice, creating localized dense and less dense regions that lock the ridge. With proper parameters, the molten pool flows into the joint corners smoothly. The Marangoni effect drives molten metal toward the hottest region, so the bead fills without collapsing or leaving a dish. No wire is needed, because the pool self-levels. The liquid metal chases the heat source and balances itself. If the heat is too low, the pool freezes before retracting. If too high, convection exaggerates and defects appear. So, the same principle applies. Molten metal migrates toward the hottest spot, whether you're brazing from the underside or running a clean autogenous laser weld on the top side. I hope this helped you understand what is causing the dishing and how you can avoid it in laser welding. Thank you for watching. If you liked the content, please subscribe. It means a lot. I look forward to seeing you in the next one.